Okay. At the last seminar, we discussed the inclusion factor. This inclusion factor has a left adjoint, and now we will talk about sheaves, and as etal spaces. Sheaves as etal spaces. Any bundle P from lambda f, where f is a sheaf, and lambda f is a set of all stocks of sections of f, and we have a bundle, and this bundle is always a local homeomorphism. But conversely, it is also true any such bundle can be interpreted can be interpreted as a sheaf. Okay, and we will start with the definition. And I want to define an etal bundle, a bundle P. Sorry. Bundle P is said to be etal or etal cover over X when P is just a local homomorphism. It means that to each E from E there exists an open neighborhood, an open set which contains E, and V is a subset of E, such that PV is open in X, and also the restriction of P on V is a homeomorphism. Okay, and easy and example. For example, this is a covering map. Any covering map is so. Any covering map is an etal map. A non-example. For example, trivial one-dimensional real bundle. Trivial one-dimensional real bundle. This is not metal. Okay. Also notice the following easy fact, that if we have a bundle and it is a tau, and U is an open set, then we can form the pullback and we will obtain also a tau cover over U. It is also a tau cover over U. Okay, and now I formulate the following obvious proposition. For P, which is a tau bundle, both P and all sections are open maps, and all sections of this bundle are open maps, and also we can think about this object as about covering map, and as in this case we have that through every point E in E there exists at least one section and the images SU of all section form a base for the topology of E. And also, if S and C are two sections, then the following set W, which consists of all x such that S of x equals C of x, is open. Okay. And the next important theorem states that there exists adjoint factors between the category of bundles over X and between the category of sheaves over X. That is theorem for any topological space X, there exists a pair of adjoint factor such that we have the following. The category of all bundles over X, and the category of sheaves, and the functor gamma, and the functor lambda. Gamma assigns to each bundle P assigns the sheaf of all cross sections. A sheaf of all cross sections of Y, and lambda assigned to each pre-sheaf P, the bundle of germs of P, the bundle of germs of P, that is the bundle lambda P to X, and germ S at X maps to the X. Okay, and also there are the following natural transformations. At eta P, from P to gamma lambda P, and epsilon Y. This is a unit, and this is a co-unit of a junction, and this is for all P is a press sheaf, and for all Y bundle space. And hence lambda is a left adjoint to gamma, and also we can ask when this junction gives us an equivalence between the categories. This is so when if we will restrict to the ethyl bundles, and we also consider sheaves, but not just press sheaves, but sheaves. And then we will obtain an equivalence between these categories, between the corresponding categories. If P is a sheaf, then eta P is an isomorphism. Also, if Y is ethyl, then epsilon Y is an isomorphism. Okay, let's prove this theorem. Notice that the map at P was constructed at the was constructed, and it sends the function S from PU to S dotted. This is a section of the bundle from lambda P over open set U. And we should construct the map epsilon y, construct epsilon y. For do this, given a bundle, y to x, and each point of the bundle lambda gamma y has the following form: S dotted x. S dotted x is a point of the bundle lambda gamma y. Okay, and x belongs to x. S is a function from U to y, and S dotted x is the same as a germ S at the point x. And we will set epsilon y over S dotted of x just S of x, S of x in y. S belongs to the sections over U. And one can verify that this is a correct definition if for some other section T we'll prove that this definition is correct. If for some other section T we have the same germ, that is S dotted of x is the same as T dotted of x. It follows that S equals T on the open neighborhood of the x, and it implies that S of x is the same as T of x, and it's okay. Okay. The next step, one can verify that epsilon y is a continuous, and thus it is a map of bundles, and it is also natural on y. It's true. And the next step, this space lambda gamma y is in general bigger than y, because if we take a vector space, then we can find that there are sections which can have one common point, and thus this space in general much bigger than y. But if y is étal over x, then y epsilon y is an isomorphism, and we should write the following: if y is tal over x, then epsilon y is an isomorphism. Let's prove this statement, and to do it, we will construct the map theta y, which is an inverse map, and we will define it as follows: for any y from y with this property p of y equals x, there exists an open set an x, and also there is a cross section. There is a cross section S from U to Y, such that S of X equals Y. This section is just passes through Y, and then we can define this map theta Y of Y is just S dotted of X, where S is the section, S dotted is a germ, and germ at X. S dotted of X is just a germ of X at the point X, and it belongs to lambda gamma Y, and we can think about this one as a take a stock, and this one is just take a section. We take a section, and after that we take a stock, and we will obtain this thing. Okay. It is a correct definition of theta y, and also theta y is continuous, and thus we have proved that in this setting, when y is a tal over x, we have that epsilon y is an isomorphism. Theta y is an inverse to the map theta y. Okay, and now I want to prove that epsilon y and eta is actually natural transformations, and we should verify the triangle identities. We have the following composition. We can take lambda, we apply this, we will obtain lambda gamma lambda epsilon composition with epsilon, and what is the composition? We have a germ S at X. It maps to the S as dotted at the point X, and this maps to the this one. I recall that eta adds a dot, and epsilon removes the dot. Eta is a map, and the epsilon is such map that okay. I recall what is eta and epsilon, and we have the following composition, and hence this composition is an identity. This composition is an identity, and also we can consider another composition. And the section S from gamma y of u maps to the germ S, and it maps after that to S, and this composition is also identity. And thus we obtained triangle identities, and thus eta and epsilon are respectively unit and co-unit of the junction. Okay. And now we can introduce the following notation. Let this is a etal x be the full subcategory of the category bundle of x, which is a all continuous maps from topological space to the fixed topological space. X is just over a category consistent of etal bundles. Okay, then we have the following corollary. The functors gamma and lambda from the previous theorem restrict to the equivalence, restrict to an equivalence of categories. The first one is a category of sheaves on a topological space X, and the category of all etal bundles over X. And also we have the following. We know that this the category of sheaves is reflective in the category of pre-sheaves, but also the category of etal spaces is a co-reflective subcategory of the category of bundles of X. Is co-reflective and is reflective. That is this inclusion factor has a left adjoint, and this inclusion factor has right adjoint. Okay. Now the proof is obvious. Okay. And now I want to.
What is the right adjoint to the inclusion factor from tau bundles to bundles?
Okay. What is a joint factor? Mm-hmm. Mm-hmm. I don't now. I don't know, but I can fix this question. What is this factor, this inclusion factor is okay. This factor has as left adjoint the factor gamma lambda. Yes.
Yes, yes.
And in this situation, I think perhaps perhaps this one.
Okay.
Okay. So sorry. Thank you for the question. I think so, but I'm not sure.
Oh, it looks believable because you get certainly you get in a tau bundle after taking sections and then taking stocks, right? So lambda is always in a tau space over X, right?
Yes.
So then this is certainly this is a functor from bundles to tau bundles over X.
Okay. We can continue. Now, more conceptual way to construct the bundle per sheaf. More conceptual way. to construct the bundle press sheaf. Bundle press sheaf adjunction. It is the following way. For any open set U, we can we have inclusion U to X, and hence functor. We have a functor. Functor A from the category of open sets to the category of bundles over X. And what is a functor? This functor sends U to the inclusion. And we have the following diagram. By United Embeding, we have this map to the press sheaf over X, and we have also functor A, and there is a functor R, and we will define this functor in the following way. R of U R depends on the bundle P, and the R of U is just a home and we can notice that this is maps from this one to this, and over in this category, and it means just that this is a section. This is a set of all sections over the open set U. Just the set of cross sections of P over U. So R of P is just gamma of P, is a cross-section functor. Then we can apply the theorem which was mentioned in Grisha's talk, the following theorem. I recall it. Let A be a functor from the category C to E. We have the following diagram. We have the following diagram, and the functor from a small category to a complete category. Then the functor R from E to R from E to sheaves over sheaves on C has a left joint, and this is a following function. R of E sends C to the home, the following home. And this functor has a left joint L from between these categories. And this functor is determined by a colimit formula. Okay, and from this theorem follows that there exists a left adjoint lambda prime, which is some colimit. And thanks to uniqueness of junction, we have that lambda prime is equivalent to lambda. Okay. And the next important corollary tells us that every sheaf can be viewed as a sheaf of cross sections. Proof. It's quite easy. Modular the model these theorems, and for a sheaf F, consider the associate étale bundle. Lambda F or lambda sub F to the X, and we can replace the functions. Replace functions from FU by the isomorphic set of sections of this bundle. By the set of sections of lambda F over U. Sometimes I will write lambda F, or which is the same, lambda F like this. Okay, and thus we can assume that each element S is just a section. Just a section as dotted from U to lambda F. And if we have an inclusion of open sets, then we have the restriction map FU to fw, and for this map we can consider the restriction map of a section, the restriction map of sections, and this map gives restriction map of a section. Okay. Thus, we have the following identification. For each S, we can consider as dotted. As dotted, such that as dotted of X is just a germ of S at X. And now we want to characterize morphisms between sheaves. And to do this, we have the following corollary, which tells us that, which describes morphism between sheaves. A morphism H from F to G between sheaves can be described in any of the following three equivalent ways. The first one, this is a natural transformations. Between these functors. And the second one, this map is a continuous map between bundle spaces lambda F and lambda G. And the third one, as a family of the maps, I recall that we have the following diagram. H is a natural transformation, and we can send this to the following map. The vertical arrows just are taking a germ, and the map H induces the map HX between germs. Okay, and this is a family of functions on the fibers, over each X, such that the following condition of continuity holds. That is, for any open U and for any section S, the function, the following function, which sends X to HX of S of X, is continuous. This condition can be reformulated in the following way. We'll say that equivalent reformulation we consider this map and such that the composition H and S is continuous on U for all S from FU. Okay, let's prove this corollary. The equivalence between point A and B is obvious. Follows from the previous theorems. And now we should and now we should verify that that there is an equivalence between the condition 3 and 1 or 2 given given the map HU natural transformation, and we have and we want to determine the functions. Determine the functions hx between fx and gx. And we want to prove that this this function is continuous. Now I think I can skip it. Okay. It's very interesting, but I think I can skip it. Okay. And now the next interesting theorem tells us that this reformulation in this point we can use to understand whether this map is epi or mono, and we should consider the fibers on restriction on fibers proposition, a map between sheaves. This is a sheaves on a space X is an epi or mono in the category of sheaves on X if and only if for all X the map of stocks Hx from Fx to Gx is surjective or injective respectively. Okay. And to prove this, we can we should introduce the following functor. This is a skyscraper sheaf functor. Skyscraper sheaf functor. For each set A, for each x in x, sky of u, a of u, is a if x belongs to u and 1 otherwise, where 1 denotes some fixed one element set. Okay, and for inclusion of open sets, we have the map. We have the map. And it is just identity map if x belongs to u, and the following unique map if x, not u, but belongs to v. Okay, and x doesn't belong to v. Okay, and thus this is a functor, contrarian functor, and we have the following important lemma. For any x stock at x, which is a functor from the category of sheaves to the category of sets, is a left adjoint to the skyscraper sheaf functor. From the category of sets to the category of sheaves. Okay. We will describe the bijective correspondence. Proof. We want to obtain the following correspondence between set functions phi from fx to a, and the set of sheaf maps h from f to sky a at x. And for this function, we can define the following function h by components. Hu is the following function. It is a unique map from f of u to 1 if x doesn't belong to u, and it is a otherwise h of s is a phi of germ s at x, and it belongs to a, which is the same in the situation when x belongs to u. It is the same that sky at x. for any s function from f of u. And conversely, for a map from f to sky at x, we have a map phi which sends the germ at x to hu of s, which belongs to a. And a is the same as a sky at x of u. And one can verify that these maps these definitions are correct, and these maps are inverse to each other. Okay, and now we can prove the proposition. Now we can prove the proposition. First of all, in this direction, suppose we have this map is a map of sheaves such that each stalk is surjective. We have a surjectivity on the level of stalks, and why h is epi. Okay, consider the maps K and L from G to H such that KH equals LH. And then we can take a stalk at X. Take a stalk at X. Then we obtain the following. We take a stalk at X in this, and this side, this left side, and this is the same as a composition stalk of the composition, and because of this identity, we have that this is the same as the following, and also it equals to the following, but hx is surjective. Hence, we can remove this one, and we will obtain that stalk k at x equals to the equals stalk L at x, but K and L are determined by the determined by the effect on stalks. and it follows that K and L is the same, are the same. Okay, and for Mona, we can use the same. We can prove in the same way. In the case of monic maps, but in the other direction, let H from F to G be an epimorphism in the sheaf category. And now prove that each stock map now prove that each stock map is epi. It's quite easy. We know that stock functor. We know that the stock functor has a right adjoint. And it is a sky functor, and hence stock functor preserves colimits. But the condition that H is epi is a condition that the following diagram is a push-out diagram. But push-out is a colimit, and hence we can and hence the statement follows in this case. And if we consider the case of monos, then the condition that H is a mono in the sheaf category is the same that we have the following pullback diagram. But pullbacks in the category of sheaves are computed pointwise. Pullbacks are computed pointwise in the category of sheaves, and thus we have the following pullback diagram in the category of set: f of u to g of u. Thus, it follows that HU is injective. for all u. But then suppose that hx of germ of s at x equals germ of c at x. Then by definition of then from the following commutative square, we have that germ of hu at x equals germ hu hu of s, hu of c, and we have the following equalities. Thus, if I have the quality of germs, it means that we have at some small neighborhood equality of the functions. For some smaller neighborhood w from u intersects with v, we have that h restricted to hu of s restricted to w equals hv of s restricted to w, and thus we can apply the naturality of h, and we have the following: hw of s restricted to w is the same as hu of s restricted to w, and this is because of this quality we have the following quality, and now we apply the neutrality, and now we have obtained that we now obtained the following quality, and but we know that hw is injective. It was proved here and thus we have that s restricted to w is the same as c restricted to w, and this condition is the same as a equality of germs at the point x. And it means that hx is an injective map, injective function. Okay. And now we can start discuss the next topic. The next topic is sheaves and with algebraic structure. And in algebraic topology or in algebraic geometry, we have homology and cohomology with local coefficient system, and sheaf homology, and coefficient groups is often be taken locally, and this is a main motivation of the topic. And definition, give the following definition. In any category C with the finite products define an abelian group object, of C to be an object A together with three arrows, three following arrows, A to A times A to A is a abelian operation. Inversion and also neutral element. And also we consider all diagrams for associativity, commutativity, and etc. laws. Then in this setting, we say that a sheaf P of abelian groups on some topological space X is defined to be an abelian object in press sheaves. And equivalently, we can say that sheaf of abelian groups is an abelian group object in sheaves that is functors from the opposite category of open sets to the category of abelian groups, for example. F is a sheaf F is a sheaf of sets. And we also have the adjunction between the following categories. What does it mean? It is a notation for a bundle of abelian groups. A bundle bundle of abelian groups over X is we can consider bundles over X, and we can suppose that each fiber is has an operation, for example, addition, and in each and we can take products in products of the bundles. If we have this bundle, we can consider a product of this bundle with itself, and we will obtain the following pullback. And this pullback tells us that we consider we consider each fiber, and each fiber is a each fiber has some algebraic structure, and this structure for each fiber. Okay. Or equivalently, a bundle of abelian groups can be defined as a bundle in which each fiber is an abelian group. Is an abelian group. It's a natural definition. Okay. And our global aim, the next aim is to prove that the category of sheaves on X is an elementary topos. And to do this, we should verify some conditions, and for example, we should verify that we should verify the following: this category has all finite limits, and also co-limits. The next point is that category of sheaves has exponentials. And sheaves has a subobject classifier. But this condition, these conditions will be verified in the next seminar, I suppose. Okay, thank you. Have you questions? Oh,
Oh, no, I don't have any questions.
okay.